The race for electric vehicle dominance used to be entirely focused on the battery. How far can it go? How fast can it charge? That narrative is fundamentally changing. Today, we are shifting the spotlight entirely to the power delivery system, which is evolving faster than almost any other component in the EV ecosystem. We are talking about the electric drive system.
And we are taking a deep dive into an absolutely essential piece of industrial literature, the electric drive system technology roadmap, or as it's called, RoadMap 3.0.
Wow.
And this isn't just, a collection of technical specifications. This is a strategic blueprint.
The mission of this deep dive is clear. We're going to analyze this colossal industrial strategy, and it really does read like a high-level consultancy report, to understand the full 15-year plan. What are the current achievements? What are the technical pathways to the future? And I think most importantly, what is the strategic intent?
The intent is monumental. I mean, the core goal, as it's defined right there in the source material, is to shift an entire industry structure from its current position of global parallel running.
So just keeping pace with everyone else.
Exactly, keeping pace with international standards to establishing full global leadership by 2040. And this entire strategy, it really hinges on deep multi-domain integration and achieving strategic resilience over the next 2 decades.
Okay, so before we unpack that huge 2040 vision, we need to clarify our terms. When we say electric drive system, what specific components are we actually covering here?
It's the entire core of the new energy vehicle, or NEV, powertrain, but it's viewed as a complete system, not just a collection of parts. It covers the upstream foundation. So specialized raw materials like high-grade silicon steel and advanced permanent magnets, and critically, the necessary chips and control software.
So right down to the fundamental building block.
Right. Then it moves through the physical system, the motor controller and power electronics, the transmission things like the reducer or gearbox, and then finally the assembly process and vehicle integration. It is a full life cycle industry chain perspective.
And this RoadMap 3.0, it seems they've redefined how they even look at this chain. They've moved from older, more fragmented models to what they're now calling a 5-in-1 framework. That suggests a new strategic organization for innovation.
Precisely. This 5-in-1 architecture is meant to coordinate innovation across the entire ecosystem, and it defines the scope of this whole roadmap. First, you have the foundational components, the drive motors themselves.
Okay.
Second, the digital control units, the motor controllers. Third, and this is a new, really crucial focus area that reflects the shift to higher voltages and integration, the power electronics assembly, or PEA. And that wraps in things like the onboard charger, the OBC, and the DC-DC converters.
Got it.
Fourth is the integrated unit, the electric drive assembly, and that covers centralized, distributed, and hybrid configurations. And then the fifth pillar, which to me shows a huge strategic shift toward governance and supply chain control, is testing, evaluation, and green manufacturing. This is all about ensuring sustainability, quality control, and frankly, standards dominance across the whole chain.
Okay, so let's unpack this blueprint. Before we can even look forward to this idea of global leadership in 2040, we need a credible baseline. Where exactly does the industry stand right now, having just completed the ambitious 2025 goals set by the previous roadmap?
Well, the current status report is very direct about this. It says the industry has largely met or even surpassed the stringent 2025 technical targets from RoadMap 2.0, and this achievement is not trivial. It establishes a very robust foundation, and it confirms that they are, as we said, currently running parallel to the most advanced international standards. They've built the launch platform for the next leap.
Let's zero in on the motors then, the hardware component that actually converts electrical energy into motion. What are the key performance indicators, the KPI triumphs, that we've seen in mass-produced EV motors?
The advancements are primarily in 2 areas, power density and speed. The previous 2025 target for motor peak effective mass power density was set at 5.0 kilowatts per kilogram.
Okay, 5.0 kilowatts per kilogram.
Okay, 5.0 kilowatts a kilogram.
Oh.
The industry has already blown past that. They're achieving mass densities in the range of 5.5 to 7.2 kilowatts per kilogram in high-end passenger vehicles.
Wait, 7.2 kilogram. That's nearly a 50% increase over the 2025 target for some models. They didn't just meet it, they smashed it. What specific engineering changes are driving that massive jump in power output relative to the weight?
It's a combination of 2 major factors, rotational speed and coil packing efficiency. We've seen the highest rotation speeds increase dramatically. They're now hitting 20,000 to 22,000 revolutions per minute.
Wow.
And you can think of it this way. For a given amount of torque, The faster you can spin the motor, the more power it produces. That speed increase is just fundamental.
And more speed means you need to maximize your copper utilization, I'd imagine. That brings us to the winding technology.
Correct. Concurrently, the use of flat wire winding, which is known generically as hairpin or eye-pin or S-winding, is now the dominant technology. This design allows for up to 10 layers of winding, which drastically increases what's called the slot fill factor.
Meaning you're just packing more copper into the same amount of space.
Exactly. More copper packed into the motor slots. And this improved packing increases efficiency and the thermal management capacity, which enables that higher power density without making the motor any bigger.
So faster spinning rotors and denser copper packing are the physical drivers. But to sustain that kind of performance, you must need high-end material science. What's the current status of materials like specialized steel and magnets?
The material progress is steady and, really importantly, scalable. That's a major victory for the supply chain. We're seeing low iron loss silicon steel, which minimizes energy waste. We're seeing low, heavy, rare earth permanent magnets, which address cost and geopolitical risk, and high-grade insulation materials being applied at a large scale. However, the report is very candid about the shortcomings.
Oh, interesting. What are they?
It says the material quality, especially concerning the insulation systems, the high-speed bearings, and the resulting noise, vibration, and harshness, or NVH characteristics. All of that still requires aggressive improvement. The goal is to ensure long-term reliability and market acceptance at these extreme new speeds.
So the roadmap is basically acknowledging that speed and density create new problems you have to solve, like noise and wear. Okay, moving from the motor to the controller, the brain, this is where the silicon carbide revolution has truly taken hold, isn't it?
Absolutely. The motor controller breakthroughs are completely inextricable from the adoption of silicon carbide or C-type devices. The industry not only met the 40 kilowatt per liter volume power density target for 2025, but they've pushed past it, achieving 35 to 45 kilowatts per liter in mass production today.
What's the so what behind C for the driver? Why should they care about that?
Well, CSIS fundamentally reduces energy loss during the power conversion process. We're seeing peak efficiencies of 99.0% to 99.3%.
That's almost perfect.
It's incredibly high. And this is critical because nearly perfect efficiency means less heat is generated, which allows for smaller, lighter cooling systems. And on top of that, CC is just inherently better suited for the higher switching frequencies and higher voltages, specifically the 800-volt high-voltage platforms that are becoming standard for fast charging.
And these controllers, they have to meet some pretty stringent safety requirements, especially as high voltage becomes the norm.
Oh, that's vital. The controllers meet a very high bar for functional safety. They're achieving ASIL-CD ratings. And for the listener, ASIL-D is the highest possible automotive safety integrity level. It's essentially the mission-critical standard for systems where a failure could result in life-threatening harm.
Right.
They also meet cybersecurity level 2 or above, so this ensures the digital control layer is just as robust as the physical hardware.
Okay, so that moves us to integration. We are, I think, well past the era of having separate boxes for the motor and the controller. What does the current multi-in-one integration look like today?
Centralization is the clear mainstream. The basic 3-in-1 assembly, which integrates the motor, the controller, and the transmission or reducer, that's the global standard for passenger vehicles. But the trend is already moving toward multi-in-one assemblies that incorporate the entire power management system.
So we're integrating the power electronics that charge the car and manage its internal voltage systems too.
Exactly. We're seeing the OBC, the onboard charger, the DC-DC converter, and the PDU, or power distribution unit, all being packaged into the central drive assembly. This deep integration is driven by spatial constraint. You want less space, less weight, and the benefits are already there. Volume reduction of 15 to 20% and weight reduction of 12 to 15%. This packaging revolution directly frees up critical space for batteries or for the passenger compartment.
And the sources even cite an external benchmark here. The competitive environment is obviously relentless.
It is. They highlight the competitive ceilings set by players like Lucid Air, whose 900-volt system achieved an astonishing 6.8 kilowatts per kilogram for its entire drive unit. And that's a clear signal that, while the industry has met its 2025 targets, the true high-performance global standard is constantly being redefined. It demands even more aggressive targets for the next 15 years.
Before we jump ahead to the 2040 vision, let's briefly touch on the cutting edge. Distributed drive systems. Are in-wheel motors still just an engineering curiosity, or are they a genuine architectural shift?
Right now, I'd say they are in the early, very high ambition stages. Distributed systems, which include in-wheel or wheel-side motors, are beginning to appear. They're integrating steering and braking directly at the wheel. Companies are already demonstrating high torque and power densities in prototypes. However, the roadmap is very clear that widespread commercialization is being hampered by some critical engineering challenges,
Like what?
primarily related to managing unsprung mass and, crucially, durability. In particular, creating durable, high-speed bearings and dynamic seals that can survive the harsh environment of an exposed wheel assembly. This technology really needs to be proven before it can be scaled.
Okay. So a lot of progress, but still a long way to go on that front.
What's fascinating here is that the overall strategy is far more profound than just improving individual metrics. The report explicitly frames the future strategy as an ECWR, an ecosystem-building exercise aimed at achieving comprehensive global leadership by 2040. This goal is hinged on two enormous, interwoven strategic pillars.
Let's start with Vision Pillar 1, which focuses on industrial autonomy and supply chain resilience, mastering the technology chain and innovation chain.
This is a geopolitical and strategic statement as much as it is a technical one. The goal is to build a complete, self-reliant ecosystem from the ground up, from the materials and chips all the way to the final assembly. It is about establishing complete domestic control over bottleneck components in the supply chain to ensure resilience and security against any external shocks.
So what specific components are considered these critical bottlenecks that they feel must be mastered domestically?
The focus areas are explicit, and they really define the future R&D priorities. High current density power semiconductors, so that means the next generation of SASE and ultra-wide bandgap devices. High thermal resistance capacitors, which are necessary for high frequency operation. High compute system level microprocessors, or MCUs. And non-rare earth or low heavy rare earth magnets. This investment is about securing the industrial core that's required for self-sufficiency and full life cycle control.
Okay, that addresses the physical hardware and materials. Vision Pillar 2 seems to focus on redefining the vehicle's architecture through integration.
Vision Pillar 2 is about new architecture and domain control fusion. The objective here is to redefine vehicle dynamics and control through deep multi-domain integration. This means integrating the physical systems, like distributed in-wheel drive, with the intelligent by-wire chassis systems, so steer-by-wire and brake-by-wire.
And multi-domain isn't just physically putting them together, right? It's managing all the resulting interactions.
Well,
Mechanical, electrical, thermal, and noise.
precisely. It is the fusion of power domain control, using those powerful new MCUs, to ensure high ASIL-D safety standards and intelligent, seamless control across all these integrated systems at the same time. This is the real shift to the software-defined vehicle, starting right at the heart of the powertrain. This architectural change allows for far greater optimization and performance upgrades after the car is sold.
This strategic climb requires some very clear milestones. The report breaks this 15-year push into a defined three-step development strategy, moving from 2026 all the way to 2040.
And these steps, they provide accountability for such a massive industrial undertaking. So phase one, the near term from 2026 to 2030, is the engineering application stage. Key materials and devices must see validated breakthroughs and begin engineering application. Critically, the MCU and domain control architecture achieve engineering application status.
So what does engineering application mean in practice? Like, it's working in a lab but not on the road yet.
Sort of. It means it's proven, it's validated, and it's ready to be designed into the next generation of vehicles. It's past the research phase. In this phase, distributed systems must achieve integration with intelligent by-wire chassis. And significantly, the first major sustainability target is set here. Overall, recyclability should reach 50%. This shows that sustainability is not a late-stage concern, but an immediate industrial priority.
Okay, and phase 2 is about industrializing those validated technologies, I assume.
Correct. Phase two, the midterm, from 2031 to 2035, is the scaling production stage. Performance continues to improve, and the key achievement here is that distributed systems, especially in-wheel and wheel-side, achieve mass production. A complete standards and evaluation system is established across the industry chain, and recyclability takes the next step, targeting 60%.
And finally, 2040 full leadership.
Phase three, The long term, from 2036 to 2040, is the full leadership stage. This is when the industry is intended to solidify global dominance. MCU and domain control achieve large-scale application, fundamentally defining the vehicle's intelligence. Distributed production volume expands significantly, cementing this new architecture. And the final sustainability goal is achieved, a 70% recyclability rate.
The ultimate success of this whole strategy is defined by some, frankly, astonishing key performance indicators, or KPIs. Let's look at the numbers that are meant to define global leadership by the year 2040.
These targets represent a quantum leap from today's standards. For the performance car motor power density, the target is set at greater than or equal to 18 kilowatts per kilogram.
18. To put that in perspective, today's high end is around 7.2 kilowatt calories. That's more than doubling the power density in 15 years.
It's a huge jump. The controller volume power density must reach greater than or equal to 120 kilowatts per liter. The newly emphasized power electronics assembly volume power density, that's the integrated charger converter unit, is targeted at greater than or equal to 70 kilowatts per liter. The overall centralized drive assembly power density must maintain high efficiency, targeting greater than or equal to 5.0 kilowatts per kilogram. And for hybrid systems, the passenger vehicle hybrid torque density must reach greater than or equal to 32 newton meters per kilogram. These are, the engineering definitions of absolute world-class performance.
All right, let's zero in on the engineering detail needed to hit those targets. We need to drill down into the technology roadmaps for the core 5-in-1 domains to see how, for instance, a motor can realistically hit 18 kilowatts per kilogram.
The Drive Motor Roadmap is a masterclass in thermal management, material optimization, and noise reduction. That 2040 performance car motor goal of greater than or equal to 18 kilowatts per kilogram peak power density, that requires massive leaps in every single physical attribute. And this performance must also be delivered with whisper-quiet operation, with noise, vibration, and harshness, or NVH, levels targeted at less than or equal to 70 decibels.
That noise goal is almost as challenging as the power density goal. We're talking about a motor spinning at over 20,000 RPM while producing huge power. Noise reduction there has to be a direct consequence of improved material quality and precision.
Exactly. And for commercial vehicles, the focus shifts to robust power output. High-torque motors need to achieve a density of greater than or equal to 30 newton meters per kilogram. This requires specific breakthroughs in key materials, and it's heavily driven by that imperative of supply chain autonomy.
Okay, let's discuss the first material breakthrough. Silicon steel. This is the backbone of the motor core. Why is its performance so critical, and what is the target?
Silicon steel is crucial because it directly influences iron loss. That's the energy wasted as heat due to alternating magnetic fields. The 2040 goal is highly specific. The P1.0400 EO indicator, which measures iron loss at 1.0 Tesla and a 400 Hz frequency, must drop to less than or equal to 9 watts per kilogram. The increase in power density means higher magnetic flux and higher switching frequencies, which just magnifies this loss.
So lower iron loss means less heat, which allows us to push more current through the motor and achieve that 18 kilowatt per kilogram density without, melting the component.
That's the link. That is the fundamental link. To achieve this, the focus is on developing high-strength, low-loss materials, things like 6.5% high silicon steel, or even exploring amorphous materials and perfecting their rolling and coating processes. This requires industrial mastery over the material creation process itself.
Okay, next up, the permanent magnets. This is the rare earth element challenge. The goal to reduce dependence on heavy rare earths seems like a major geopolitical and strategic move.
It absolutely is. The report mandates a drastic reduction in dependence on heavy rare earth materials like dysprosium or D and terbium TB. By 2040, the content in permanent magnets must be less than or equal to 0.3% by weight. This is an industrial strategy aimed squarely at reducing cost fluctuations and mitigating geopolitical supply risk.
But is the technology for moving to low, heavy rare earth magnets truly mature enough to anchor an entire 15-year industrial strategy on it? That seems incredibly ambitious, given how hard it is to maintain magnetic performance without these elements.
It is extremely ambitious, but the roadmap outlines the specific technical solution. It's focusing on light rare earth magnets combined with sophisticated microstructural control technology. This involves adjusting the crystal grain boundaries and optimizing the phase structure of the magnet material at a microscopic level to boost coercivity, which is magnetic force retention, without relying on heavy rare earth elements. The strategy is betting on precision material engineering overcoming elemental necessity.
Now, what protects the windings from all the heat and electrical stress generated by these high-speed, high-density motors? the insulation system.
The insulation requirements are extreme. The materials need to handle the high voltage and, more crucially, the incredibly high switching frequency up to 50 kilohertz from the 60 punch rollers. The 2040 demands are high temperature resistance exceeding 260 degrees Celsius, high thermal conductivity over 1.0 watt per meter Kelvin to pull heat away efficiently, and extreme high-frequency partial discharge inception voltage life, or PDIV life.
For listeners who aren't in the high-frequency design world, what does a 50 kilohertz switching frequency actually feel like in terms of heat and electrical stress on that insulation?
You can think of it as a constant, rapid-fire electrical hammering. Partial discharge happens when these high-frequency voltage spikes create microscopic electrical discharges within voids or imperfections in the insulation material. This rapidly degrades the material. The goal of surviving over 400 hours at 50 kilohertz is a monumental durability target. It's to ensure that insulation, which is often a failure point in high-speed motors, can keep pace with the power electronics driving the system.
And finally, the components that enable all this speed, the high-speed bearings. If they fail, the entire motor fails, and high frequency introduces a particular kind of wear problem.
It does. The surface life of high-speed bearings for passenger vehicles must be extended to greater than or equal to 600,000 kilometers. And the specific problem here is electrochemical corrosion. Stray currents, created by the high-frequency switching of the controller, can pass through the motor shaft and actually etch the bearing surfaces, causing premature failure. So the RoadMap demands perfecting anti-electrochemical corrosion technology to manage these stray currents and ensure reliability over the vehicle's massive lifespan target. Okay, so moving from the power generation of the motor to its digital control system, the motor controller RoadMap is a pure exercise in density and thermal mastery of silicon carbide.
The 2040 volume power density target for Siegel controllers is greater than or equal to 120 kilowatts per liter. As we said, today's best is around 45 kilobyte bell. We can't get much more efficient than 99.3%, so how do you physically fit triple the power density into the same volume without instantly turning the unit into molten metal?
You've hit the key constraint. It's all about thermal management. Since the efficiency gains are now marginal, that 120 kilowatts per liter has to come from maximizing power density and thermal tolerance. The strategy focuses entirely on optimizing the wide bandgap semiconductors and their packaging.
Let's focus on the Synergy devices themselves.
For 1200-volt Secure devices, the current density target is greater than or equal to 800 amps per square centimeter. And achieving this means moving away from traditional wire bonding and thermal interface materials. The goal is an intense focus on high-density packaging techniques like silver sintering and epoxy molding.
What does silver sintering achieve in this context? What's the advantage?
Sintering replaces the solder joints with a sintered silver layer, which provides a far more robust, high-temperature, and low-resistance thermal pathway. This packaging innovation allows the SiC modules to operate at extreme junction temperatures, up to 240 degrees Celsius. By allowing the components to run hotter and dissipate heat more efficiently over a smaller area, you achieve the massive density increase required for that 120 kilowatt per liter goal.
So even with C dominating, there's still a plan for silicon or Si insulated gate bipolar transistors IGBTs.
Yes. For 750-volt Si IGBTs, which are often used in less performance-intensive or more cost-sensitive applications, the target current density is still aggressive at greater than or equal to 400 amps per square centimeter. Progress continues in improving their chip design and module packaging, ensuring that Si technology remains a viable high-performance option where SiC might be overkill.
The passive components often become the physical bottleneck, don't they? Especially the capacitors, which store and smooth the power. They have to deal with these intense, fast power spikes.
Exactly. The passive components must handle the speed of the Si switching devices. For high-temperature film capacitors, the critical metric is ripple current resistance at 150 degrees Celsius, which must reach greater than or equal to 0.70 amps per microfarad. This requires developing ultra-thin dielectric films and integrated packaging to handle the high ripple currents and temperatures without the capacitor failing prematurely. If the capacitors can't handle the switching speed, the whole controller system just bottlenecks.
In sensors, the eyes and ears, they must be providing flawless data to the domain controller to manage all this complexity. How precise do they need to become?
The required precision is bordering on the extreme. Current sensor signal detection accuracy must reach an astonishing less than or equal to plus or minus 0.25% across the full operating temperature range by 2040. And this has to be combined with high bandwidths up to 5 megahertz.
Why is that level of precision so critical?
Because at these high switching speeds and power levels, tiny inaccuracies in current readings translate directly into motor instability, increased noise, and inefficient torque application. The advanced domain controller needs ultra-clean data to maximize torque output and, of course, ensure ASIL-D safety. So now we take those high-density components, the motors, the sys controllers, the sensors, and we integrate them into the power electronics assembly, the PEA, and the domain control system. This is the architectural challenge of the next 2 decades.
That PEA target of greater than or equal to 70 kilowatts per liter for passenger vehicles, that means squeezing the OBC and the DC-DC converters into a space smaller than many current power banks.
And achieving that density means redesigning the entire integrated power system for hyper-efficiency. For example, the onboard charger, or OBC, full load average efficiency target is greater than or equal to 95.8%. This relies fundamentally on multi-domain deep integration. We're talking about co-designing the electrical circuits, the mechanical casing, and the thermal pathways all at the same time, often sharing cooling loops and structural components to manage heat and reduce internal parasitic resistance caused by excessive wiring.
But the truly transformative element here has to be the brain. The high compute system level microprocessors, or MCUs, and the domain control architecture. This is the real transition to the software-defined vehicle.
This represents the shift from isolated, dedicated control units to a centralized, unified brain. The computational power required to manage all these integrated systems, especially coordinating distributed drive and by-wire chassis components, is just skyrocketing. The CPU compute power must reach 32 kilotriston million instructions per second, or 32 kDMPS by 2040. This is necessary to run real-time operating systems, virtualization layers, and sophisticated control algorithms, all on one chip.
32 kDMPS. That's a huge amount of computing power dedicated just to managing the powertrain. What specific functions does that processing power unlock?
It enables the service-oriented architecture, or SOA, compatible power domain control systems. Think of it this way. Instead of a single piece of software controlling a single physical motor, the domain controller uses virtualization scheduling and multi-core deployment to manage all power, thermal, and control aspects of the vehicle simultaneously. And this high processing power is what ensures full compliance with the strict ASIL-D functional safety requirements, because the failure of the single point of control would be catastrophic.
And the strategy states this must be an autonomous proprietary ecosystem.
Correct. The strategy demands building a robust, complete domain control architecture where the hardware and software ecosystem, from the chip design through the operating systems to the tool chains used to write the control code, is all domestically controlled. This is key to strategic autonomy and resilience. It ensures total control over the future of the vehicle's intelligence. So, moving from individual high-density components to the complete system, the blueprint shows a future where the current concept of a drivetrain splinters into highly specialized configurations. You've got centralized, distributed, and hybrid.
Even the centralized drive assembly, which is going to remain the mainstream workhorse for passenger vehicles, is under intense pressure to improve integration. What are the 2040 goals for this standard configuration?
For passenger cars, the focus is on refinement and silence. The target is a peak mass power density of greater than or equal to 5.0 kilowatts per kilogram, which is maintained through lighter materials and deep integration. And crucially, the total noise output has to be dramatically reduced, aiming for less than or equal to 72 decibels. This requires advanced solutions, including active noise cancellation strategies managed by the domain controller and further mechanical integration to eliminate sources of vibration.
And the commercial vehicle market, which relies on heavy-duty hauling, that must prioritize brute torque and durability. How do their centralized drive assemblies change?
They rely on the e-axle concept. The torque density targets are enormous. Light truck e-axle torque density must hit greater than or equal to 90 newton meters per kilogram, and for medium or heavy trucks, it must reach greater than or equal to 115 newton meters per kilogram. The engineering focus here is platforming standardizing components so that different vehicle classes can use variations of the same e-axle module, and integrating multi-gear transmissions directly into the e-axle housing for optimal efficiency and performance under varying loads.
Okay, now let's look at the true architectural shift, the distributed drive assembly, the in-wheel or wheel-side motor systems. This promises unprecedented vehicle dynamics, but it also presents some fundamental engineering challenges.
For passenger car in-wheel systems, the 2040 targets are high. A torque density of greater than or equal to 27 newton meters per kilogram and a peak efficiency of greater than or equal to 95%. The engineering hurdle here is not the motor itself, but the fact that placing the motor inside the wheel significantly increases the vehicle's unsprung mass.
And increased unsprung mass notoriously impacts handling, ride comfort, and suspension durability. That's always been the killer for this technology, right? How does the roadmap plan to overcome this defining challenge?
The solution is mandated integration. The roadmap specifically demands deep integration with all intelligent by-wire chassis systems, braking, steering, and suspension. The high compute domain controller must actively compensate for the increased unsprung mass in real time, managing damping and steering feel entirely through software.
And the durability of components exposed to the elements. That seal life requirement for in-wheel motors is astonishing.
It is the defining failure point. The target for dynamic seal first replacement mileage is greater than or equal to 200,000 kilometers by 2040. For a component placed directly in the road, grime, heat, and vibration of the wheel hub, this demands unprecedented levels of material science and sealing technology. If they fail to meet this goal, the commercial viability of distributed drive systems remains limited by maintenance costs and complexity.
What about the wheel-side systems? They maintain some of the dynamic benefits without the full unsprung mass penalty of in-wheel motors.
Wheelside systems, or twin-motor electronic differential systems, are highlighted as a key development direction for high-performance intelligent passenger vehicles. They target a peak mass power density of greater than or equal to 5.5 kilowatts per kilogram and offer superior vehicle dynamics through torque vectoring, which is the ability to precisely control power to each wheel individually. This is where the fusion of the power domain controller and the chassis controller truly maximizes performance.
And finally, hybrid systems. They are obviously critical for stabilizing the energy transition. How must mechatronic-coupled power assemblies evolve?
They have to become far more compact and integrated. By 2040, the goal is to reduce their volume and weight by 35% compared to 2025 levels, while achieving a peak mass torque density of greater than or equal to 32 newton meters per kilogram. The focus is on integrating the mechanical, electrical, and thermal domains into a seamless unit and developing sophisticated control strategies that manage the energy flow and shifting to extract every last bit of efficiency from the combined system.
Okay, moving to the fifth and final pillar one that often gets overlooked in technical discussions, but is strategically vital: testing, evaluation, and green manufacturing. This pillar ensures the sustainability and the quality of the entire ecosystem.
This newly emphasized domain is the key to gaining future competitive advantage by defining the environmental standard. The 2040 green manufacturing targets are unambiguous. Production carbon emissions must be reduced by 50% compared to 2025 levels, and the overall recyclability rate must hit a demanding 70%.
That 70% recyclability target demands a completely different approach to component design. You have to design for disassembly and material recovery from day one.
Exactly. It requires establishing a complete standard and evaluation system covering the entire product lifecycle, including a full lifecycle assessment, or LCA, and an industry chain carbon footprint evaluation. By establishing these standards, they gain green standard dominance. The industrial mandate is to systematically improve the recycling and remanufacturing industrial chain for all key materials: rare earths, silicon steel, and core components like motors and controllers to close the loop on resource management.
And the emphasis on digital testing and simulation to achieve quality control is equally rigorous.
The goal is to maximize digital testing to drastically reduce the cost and time of physical prototyping. The virtual simulation accuracy target is set at an almost perfect 95%. Furthermore, integrating artificial intelligence is critical. AI-based health monitoring precision must reach 90%, which enables true predictive maintenance and better overall lifecycle management for these highly complex integrated systems.
So we have the strategic vision, the 15-year milestones, and the deep technical specifications across all 5 pillars. But the report concludes by highlighting 3 strategic imperatives: the actions required to bridge the gap between this technical blueprint and realizing comprehensive global leadership.
And these 3 imperatives, they represent the strategic policy drivers required to create a difficult-to-imitate and surpass competitive advantage in the global market.
Imperative 1 is about achieving self-mastery, master core technology autonomy. This links directly back to the materials and chips we discussed earlier.
This is the foundation of resilience. The industrial policy must keep R&D laser-focused on the primary bottlenecks: ultra-wide bandgap chips, low or no heavy rare earth magnets, and high-grade insulation materials. If you're in the sourcing space, this is effectively the prioritized purchasing list for the next decade. This is all about building supply chain security and independence.
And crucially, that autonomy extends to the digital infrastructure that controls everything.
Yes. It requires creating a fully autonomous software and hardware ecosystem for the system-level microprocessors and the domain control architecture. This means controlling the intellectual property, the IP, of the chip design, the operating systems, and the tool chains. If the future of the vehicle is defined by software, then autonomy over that software and its underlying hardware is the ultimate form of strategic control.
Imperative 2 shifts the focus to the new vehicle paradigm. Accelerate integration of new configurations and domain control.
This is the architectural revolution. It means aggressively pushing the deep physical and control integration of distributed drive systems with intelligent by-wire chassis components. The other side of this imperative is developing service-oriented architecture, or SOA, compatible power domain control systems.
What's the commercial impact of adopting SOA?
It allows the software-defined vehicle model to flourish. Performance upgrades and new features can be deployed rapidly via over-the-air or OTA updates, giving vehicles performance and lifespan advantages long after the initial purchase. This changes the competitive landscape from static hardware performance to dynamic, upgradable capability.
And finally, Imperative 3, which is about establishing the new competitive playing field. Build a full-chain green sustainable ecosystem.
This is about setting the bar for the entire industry. It mandates establishing industry carbon footprint standards and limits for the entire product lifecycle, that full lifecycle assessment. If you are the one defining the standards for green manufacturing and material sourcing, you dictate the terms of competition for everyone else. Furthermore, this imperative requires systematically industrializing recycling and remanufacturing to hit that demanding 70% material recovery target, ensuring resource security alongside environmental compliance.
This roadmap is clearly far more than just a list of speeds and densities. It's a strategic declaration aiming for total industrial ecosystem control. We've seen the blueprint for shifting from a parallel player to a global leader in electric drive systems. This strategy demands simultaneous, sustained breakthroughs across 5 core pillars: materials, power electronics, digital architecture or domain control, advanced system configurations, and manufacturing sustainability. The core underlying theme is deep, multi-domain integration: mechanical, electrical, thermal, magnetic, acoustic, and control.
And if you're involved in sourcing, R&D, or investment in this space, this roadmap isn't just academic. It's a clear and detailed indication of exactly where vast industrial resources and policy focus will be directed over the next 15 years, specifically into achieving component autonomy and system integration through powerful, centralized domain control. That capital will be chasing 18 kilowatts per kilogram motors, 120 kilowatts per liter controllers, and the software systems that run them.
And that leads to the ultimate question this report poses, perhaps inadvertently. The true ambition of this massive strategic effort isn't just reaching that 18 kilowatt kilogram motor density or 70% recyclability. It's about building a system so deeply integrated, so reliant on a self-controlled upstream supply chain, and so focused on full lifecycle sustainability that the resulting competitive advantage becomes, as the report implies, difficult to imitate and surpass.
The question for you, the listener, is this. When the barrier to entry is no longer just a single innovative component, but an entire highly interconnected, standards-defining ecosystem built and perfected over 2 decades, how quickly can competitors catch up? And what does that mean for the next generation of global EV competition? It suggests that the race is entering a new phase where only those with complete industrial mastery will truly lead.